not quite. Thank you for your patience, and again, people welcome to go on to the career fair here. Okay, so we're gonna review a set of best practices. Could you get the light on the left-hand side, which dims the front row? Yeah. Good. Thank you. Okay, so we're going to talk briefly about a bunch of best practices that are essential, in my view, to success in these projects. We talked about one of them last time, accountable positions, and I trust that all teams have, since that point, gone through and assigned at least a project manager, hopefully also risk officers, got some sense of who's in a testing team versus who's in development, maybe a design lead, someone who would have a technical vision about how to take it forward, and potentially an initial build master, someone who's taking charge of configuring a continuous integration system. Another thing that I will expect to see in your code up front is what is known as assertions. Now, this term has traditionally been a little bit of a confusing one to students within this class because there were some previous classes which used the term in a slightly different purpose, slightly different sense. How many people in here were in my 214 class way back when? Okay, yeah, a couple. So you would have heard me talk then about the use of assertions as sanity checks. What is an assertion? Can anyone remind me? What for those who have heard it before? Maybe you've seen it in 370. Did they cover that? 370 assertions. 270. Okay. What's an assertion? What job does it perform? So if we assert that that person is not equal to null. What is that? What job is this performing? If you see a statement like that in a Java program, assert is a statement in Java. What is it doing? What's the purpose of that?
Checks if it's true.
Okay, it checks if the assertion is true, and critically, so I like that. If it's not true, what happens?
There's something there's something gone wrong with the program.
That's right. So what this is checking, something's gone wrong, and it will signal it by throwing a runtime exception. It'll say a bad thing has happened, and critically that bad thing is a failure of a certain assumption. So what an assertion encodes in an operational form, meaning it's something which is being checked while the program's running. It's actively checking. There's an action taking place. It is establishing whether or not a programmer's assumption is true. So, look, when we write code, we make assumptions. Often, those assumptions are documented in the form of preconditions, postconditions, for example, in the form of contracts within our functions, within our methods, etc. Sometimes those assumptions are things that are more logical, having to do with the algorithm. We assume that, look, if we're at this point in the algorithm, all these things are the case. We've already done X, Y, Z. And those, you should get in the habit of, whenever you have an assumption that strikes you, either documented or implicit in the algorithm, you should write an assertion to check that. Why?
Programming errors, maybe?
Yes, they catch programming errors. Look, if your program has a problem, you want to find it as soon as possible. Right? You don't want it to stay hidden, to stay latent, that your assumption has been violated. If it's violated, you need to know that as soon as possible, because this code that you've written counts on this thing, which is not the case. So, in short, we write assertions as a form of offensive programming, of kind of going out and trying to make a broken program fail early, fail hard, so we learn from that and we can fix our assumptions. And there's lots of ways of doing this. Assertions are just the most basic in the way that I'm going to require in this class. There's many other ways. If you're working in a low-level language like C, you can fill memory allocated. before it's freed up, you can fill it with illegal values, right? Or before it's initialized, you fill it with the illegal values. Why would you do that? So you have an array, it's allocated, it's going to be done in Java too, right? It's going to be filled in, but you put in values -1 initially, say. Maybe it's going to hold indices. Each element of this array is going to hold an index, which is normally 0 or more, but you fill it initially with -1s. Why would you do that?
So you know as soon as it holds something that isn't supposed to.
Yeah, if it's using a value that's not yet initialized, you'll know it, right? You fill object with illegal data just before deletion. You know, you set certain buffers to point at the end of the heap, so if there's a problem going beyond those buffers that causes a page fault or what have you. You set, you know, if you're dealing with an enum, enumerated value, you set instances of it to use an illegal value so that you know if it's just using the default, it'll be caught. So assertions and error handling are key components of writing robust code. And they're components that will be tested in this course, not in the sense of an exam, in the sense of not primarily in the sense of an exam, but in the sense of the deliverables. And broadly speaking, assertions here catch logical errors, development mistakes, things that should never occur. They're fundamental assumptions on which, or they're assumptions on which you've based your code, and you want to know if they fail as early as possible. They are supported by languages. They're built-in keywords, for example, in Java. And many times they're stripped out of the final code. By stripped out, I don't mean they're literally removed from the code. What I mean is that the compiler can be told to ignore them. So this assertion might be operational in the code base all through testing, through development phase of the project, through the testing, all the way through acceptance testing. And then it's disabled in the final code. Or it may be left in there, but with some ability to handle it. For example, if this occurs, phone home. You know, go send post an error message to an HTTP server at the company, reporting the failed assertion, the context, what files were open, etc. So assertions should be things that pepper your code. And I expect to see, you know, in a given Java file, typical Java file, many assertions in place. At the least, they should be checking preconditions, okay? I will note that assertions do not have to be merely at this low level. You know, if a parameter that's passed is null, or if a variable in a loop has a meaningful value. They could be high-level things. So some years ago, there was a team that worked on a sort of an early version of what's now an app in place for the bus service here in town. Separate app, separate code base, but the point is they worked on similar functionality. So they created a Saskatoon bus app that would let you pick, you know, go say, I want to go from X to Y at this time. It would show you the buses you need to take. Now, that could involve 3 bus changes, what have you. So in order to create the system, they needed to define an algorithm that would, you know, go find the appropriate buses, the appropriate interchange places. And there's some combinatorics with that. There's some complexity associated with that. Because of the number of changes that can be involved, etc., you can get a lot of different possibilities. So they created what they considered a very clever algorithm for coming up with the best bus route. And initially, they had put in place a brute force algorithm, as I remember it. A brute force algorithm that just enumerated all possibilities. It was very, you know, it took a long time. It's very easy to write. You just iterate through all the possibilities. But it, you know, was expensive in terms of the runtime. So they threw that away and they put in their clever algorithm. And it turns out that their clever algorithm, as I discovered in testing it, had bugs. So it would tell me, you know, take the bus from such and such a place to Place Real and then take it downtown to the 23rd Street bus station and get off the bus and get on another bus, and immediately get off that bus and get on another bus. And had me going, off and on a bus at the 23rd Street bus station for no reason. Or their system would give, whacked out bus routing. I don't remember all the details with the problems. The point is, they could have put in an assertion that would test the results. It would do a search in the brute force algorithm and a search in the clever algorithm and test whether the results are consistent, right? Brute force algorithm, very easy to write, and it should give, in theory, the same results as the clever algorithm. The clever algorithm was supposedly should give the exact same findings, but they didn't do that. They could have. A simple assertion where you test if the results of the two algorithms are the same would have spared them me discovering this bug. They would have discovered it a lot easier. Now, why wouldn't that have been a problem? After all, it would still use the brute force algorithm. Why do I think that that's not a problem? Because these things are removed before they go to the customer. And in fact, you can disable them. You can just tell the Java compiler, disable all assertions for this version of the program, and it will basically not execute asserts. So they're very easy to disable and enable on a per module basis. So when I'm saying it's not necessarily the case that all assertions are low-level things, you could test the result of one algorithm against another, see if they're consistent, and use that to find bugs. Very easily done. Now, in addition to assertions, there's other mechanisms you're going to want for error handling. Assertions are for failures of developer assumptions. Exceptions and return codes differ from that in the sort of context that they handle. What sort of failure would be handled by these two that's different in character from assertions? Can anyone say? Anyone remember from 214? These are error handling machinery. You use a return code to say I failed, or you throw an exception. How is that different from this bottom one? What sort of failure might you use these ones for rather than an assertion?
Assertion are only used usually for mistakes that should never occur.
Yes.
An exception for they may occur.
That's right.
Errors that may occur.
Yeah, so give me a thing that you need to handle.
You ask for something out of a database, but the database is currently not available.
That's right. Yeah, I mean, look, you're not the dictator of the world where you know that the database for sure is available. In code you write here, you need to check, is that connection available? Maybe the Wi-Fi is flaky, right? And you can't get to the database right now. Maybe the disk is full. Maybe the file that the user asks you to open doesn't exist. Users make mistakes. Disks have problems. Disks fill up. Memory may not be available, right? You can't, do not think you can handle, if you're writing in C, that you can handle a null pointer returned by calloc with an assertion failure. You can't just say, oh, program bombs out because no memory is available. Sorry, that's not what a professional programmer does. You have to be able to handle this thing, maybe roll back and exit gracefully from the program at worst, or potentially alert the user that this functionality is not available, or what have you. The question is, just as Bernd said, assertions are for logical failures. These ones are for handling of error conditions that occur besides any associated with logical errors. They're inconvenient things. And I'm sorry, but we have to handle inconvenient things as software developers. Most of our attention as software developers is for the typical case, but we can't let that put blinders on for the fact that things go wrong. And in fact, what can often distinguish really high-quality software from less high-quality software is its ability to handle things when they're inconvenient, when they go wrong. When the network is behaving flakily, does this program still behave in a rigorous way? When memory is short, does the program thrash or does it behave properly, etc. Okay. So common errors caught, by assertions. Examples are here. If the heap is corrupt, there's some logical problem in your program. If there's a precondition violated, you say, in order to call this method, you need to give it a non-null value for its first argument. If that's not the case, then you need to signal that, because basically the programmer involved has done something that violates the assumptions associated with the modules that they're using, or the constructs that they're using. Logical oversights by the programmer, another type of thing, internal inconsistency of an algorithm, etc. These are the types of things you'll catch for assertions. So let me ask you to please put assertions in your code. Put them in early, put them in often. It'll be a bit of time before you get to code, but I want to see assertions through multiple milestones of this class. Okay? And they are a best practice. It's very widely used in industry. They're almost a gimme in terms of catching problems, and they can make debugging a lot more effective. Why do I say that? Why can assertions make debugging much more effective? Why can it make testing more effective?
You won't be able to run your program if anything goes wrong.
Yeah, but more than that, often when we're testing, if we're testing, let's say, a larger algorithm, hopefully it's broken into pieces, small pieces, but it's often hard to test by a test harness, calling it, what's going on internally at all different places. And that's the job of assertions. They can be peppered throughout it, and if something goes wrong, chances are, there's a good chance an assertion might catch it. So it helps provide lots of other checkpoints on the program, lots of other test points that can be validated. And similarly, when you're debugging, it can help you, catch what's going on sooner if, you get an assertion failure at this place in the code. It can clue you in, okay, maybe that's the cause of this failure that I'm observing. Okay, let's continue to talk here, though. Peer reviews. This is, in my view, one of the most important components of this class. If you go out into industry, chances are you will, within certainly a year, maybe a lot less than that, potentially in just a few months' time, undergo peer review. I go and I interview people with our internship program, because I'm one of the two coordinators of it. And peer reviews are a prominent feature of many interns' lives. Why? Because they work. It turns out testing is absolutely essential, and I expect maturity from this class in terms of putting some serious effort into testing. We'll be giving quite a few lectures which will try to give you a clue up on how you can test more effectively. But the fact is that peer reviews, at the form of inspections, formal inspections, are actually more cost effective than testing. They actually find a greater fraction of bugs than tests. And they find them with greater efficiency in terms of number of hours of human work per error found. IBM has done a large-scale study of this, and it's not quite an order of magnitude, but many binary orders of magnitude difference. In other words, testing requires a lot more effort per bug found. Testing is essential, both automated testing and manual testing in this class. We'll come back to that. But peer reviews are a best practice that easily pay for themselves in the form of inspections and in the form of other components. Now, why do these pay for themselves? Why do they pay back? Because they head off a lot of time for debugging and a lot of time for rework and fixing code. You head it off at the pass by avoiding writing code atop errors in the first place. You help lower the amount of time it takes to do the testing, to reveal the failure, and then the debugging to figure out where the fault underlying the failure lies. They're more flexible than testing. You can perform peer reviews early. You don't have to wait for executable code. You can perform it on requirements documents, on design documents. You can do it on the system requirement specification. You can do it on communications with the user. You can do peer reviews on elements of the system that are defined early, like contracts for different areas of the system. And they can be used to to really improve the processes that go on, assess communicational issues, or, for example, is this code written in a clear, transparent style? Is commenting at the appropriate level? Is the naming appropriate, etc.? Okay? So early reviews expected. I'd like to see the first reviews this month. And in fact, I think they're required as part of each exploratory talk or each milestone in this course. Other benefits of peer review. To the person reviewing the artifact, they learn about how the system works. They learn coding tricks, stylistic ideas. It spreads knowledge around in a way that testing isn't as effective. So the person whose artifact is being reviewed, well, they learn how to improve their technique. They learn about how to improve the process sometimes by which they're writing these things. And it spreads knowledge around. This is a key thing, ladies and gentlemen. Again, we spoke, I think, in our very first class about wanting to avoid points of dependency, right? Wanting to be less exposed by your bus number. You don't want to have quite a few people where if any one of them is missing, you're stuck in the water. You want to have the knowledge spread around, and this is very important. Okay, now a key thing to realize for delivering on the peer reviews for this class is I require inspections for peer reviews. These are formal peer reviews that I'm providing some slides on here. They involve preparation before the review. They have a separate person presenting than the actual author of the document. They involve later checking were the results, were the outcomes of it in fact put into place. In other words, the recommendations, were they in fact put into place when there are such recommendations. They involve multiple parties, etc. They're pre-scheduled. I've required that, and every person in this room and every person in your team needs to undergo at least one inspection in the context of this semester. I expect everyone to undergo a formal inspection of their, and I should be very careful I say that. I don't mean the person undergoes it. What I mean is the person's products undergo this inspection. So you should take place as the author in at least one inspection throughout this term. But don't get caught up to think this is the only type of peer review you do. You should be doing lots of other types of peer reviews routinely, including pair programming. How many people have done pair programming before? It's great practice. You can take a novice and put them next to an experienced programmer, and there will be learning, lots of learning going on, and not just in one way. The experienced programmer will learn from some points raised by the novice and so on. It's a great technique. Yes, it takes time. Yes, you've got two people now working on a task instead of one, but the extra spread of knowledge is often pays itself back, or the learning that goes on about how that code works and the errors that are avoided. There should also be peer desk checks going on, where you pass your code, you ask someone else, hey, could you take a look at this? Whether it's with Garrett or with hard copy, or just asking someone, go to this file in the Git repository, check it out. You should be doing lots of peer desk checks. Just get people to look at the code and comment on that in your deliverables for me. Okay, so lots of types, and they differ in whether they involve planning, preparation, meeting, verification, etc. I don't have time to go into this. This is greatest hits of best practices, but I provided some slides for you here. Okay. Okay, so let's go through these. Let's go on to some more. Incremental delivery. Okay. A key part of this class is that it's delivered in step-by-step fashion. First time I taught this class, about 10 years ago. I remember a team saying that they're going to be applying agile processes. Sounds great. Like extreme programming. Great. And a key part of extreme programming is incremental delivery. If you go, downtown to Vendasta, or you go to Point 2, or other companies around town, or other companies in the Bay Area, or anything else in the States or worldwide, what you will find is that many teams use very short iterations, very short cycles for delivery. Cycles on the order of 1 to 3 weeks per deliverable. By deliverable, I mean a fully working system with a larger or with larger feature set typically, sometimes it's just refactored, that stakeholder might look at. But in any case, it's tested, it's vetted, and it's brought back into a really robust form. 1 to 3 weeks, ladies and gentlemen, and that's what's required for this class. It's a similar type of time scale. So 5 deliverables through the semester. The team that said it was doing agile programming back in the day, extreme programming, they're supposed to be delivering every few weeks. They ended up 1 deliverable at the end, and it didn't even work properly. It was called the real-time RT pizza ordering system, RTPOS. But experience with the system suggested that the POS was had multiple meanings associated with it. The point is, iterating provides real value. And I would suggest some sort of spiral process. In 370, did you have to go through a spiral process or go through any sort of incremental delivery of a system, or was it all sort of discrete enough deliverables that you didn't really have incremental delivery going on? Did anyone say?
We did waterfall.
Oh, you did waterfall. Okay.
We learned about spiral though.
You did. Okay. So with spiral, basically you're going through multiple phases where you're doing analysis of what's needed. You are doing further planning, on sort of what needs to be put in place, how long it's going to take. You figure out what can we afford to do in these 3 weeks. Communicate. You actually do construction, development of it, and you iterate further. And there's many iterations of this. The spiral model is often applied in a risk-driven approach, where you deal with the things that are high risk early, or the things that are high priority in terms of user value, right? So you do the things that will yield the biggest bang, or the greatest will shrink the uncertainties. And each cycle leads to decrease in risk, increasing product definition, and hopefully increased value delivered to the user. I'm not particular about which particular approach you undertake, but it needs to involve rollout in a systematic way. So 5 risk and value delivered deliverables, ladies and gentlemen, this should involve each one being executable. Now, I do make exceptions, and if a team approaches me and says, "Look, there's no way we can get this thing to be working at any level for the first," I might think about that, okay. But the later ones should be complete in and of themselves. It should have a subset of features, of course, a great subset of features. They only have partial functionality. That's fine. But the point is that they are working, they are tested, they have been peer-reviewed. They are not merely a way to the bigger, better, great thing at the end of the semester. Rather, they are vetted through the system. Okay, so I do expect that in the course of this semester, and that involves some maturity about how many things we put in there. If you go to places around town, you'll find some do it on the jelly bean model. They ask the stakeholder to sort of make comments on the value of different product features, and they only have, and each of them is associated with a certain number of jelly beans, and there's only so many jelly beans to go around, and the team only has time for so many jelly beans worth of work, and there's a sort of a back and forth involving how long does it take, how much value would it deliver, how important is it for risk, for reducing the risks in terms of certain technologies. And they come to terms every 3 weeks or every 2 weeks in terms of what they'll deliver. So, in short, I want this incremental delivery. Why incremental delivery? Can anyone tell me? Give me some reasons for incremental delivery. You said you talked about it in 370, so maybe you've thought it through a little bit. Why that instead of waterfall?
Stockholders know exactly what's going on.
Exactly. So stakeholders will get updates over time. And sometimes seeing it actually changes their sense of what the priorities are. This, it took me years to really think about this because, stakeholders are smart folks. And, you think they have a vision of what they want, and and you can deliver the vision, and they don't need a lot of imagination. They must be conceiving how they want the system. But often they can't really guide you until they see something concrete, until that's in front of them. Then they'll realize, oh, I really want this more than that. And it's that feedback from them that often can occur when you have an incremental deliverable. So you give them something, you let them see it, and they say, oh, that's really interesting. What I'd really like, I said earlier this thing was next most important, but seeing this, I'd really like this other thing. And it lets them change course like that. You see what I mean? And it's really important. You might think, oh, they could, they have a mature understanding up front, they can prioritize things. Often, they're just not so involved with the technology that they can really visualize what it will be like. They can't imagine exactly how will it be captured. They can't get that clarity on what their priorities will be once they see what it actually is like to interact with. So getting it in front of stakeholders is critical, maybe the most important thing. How about another thing? Why do it in small pieces?
Prioritize parts of the product
Yeah.
has higher risks than
Good. Some parts have higher risks or higher priorities from the stakeholder perspective, higher needs, and you can get that value to them, and you can shrink those risks, right? You can take those risks, which are really broad, and collapse them, and so is this technology you're thinking about betting on going to work, or is it not going to work? You head that off early on. Remember a team that failed to do that a couple of years ago, and I think for 2 deliverables, they thrashed around because they were trying to get a certain technology that they've been really excited about working. And basically they came very close to not having success in their project because they were just banging their heads against a wall with this. There was another team that early on went after some key uncertainties. They did spike prototypes. They did sort of tiny projects that were throwaway projects, but just to test out this technology. We think it should work this way. Let's give it a try, right? Maybe you're doing collaborative software development where you have like Google Docs type of interface where if someone writes something here, the other person can see it. Sort of the thing Dr. Bosner was talking about, right? Where one doctor might put in, the nurse can see it over here. There's great libraries for that, ot.java or node.java. .js, ot.js. But, you read about these and sound great. Man, you look at some example product. Sounds like it's good match to your needs, but you really don't know for sure sometimes before you sit down and create a throwaway project that will test it out, test your understanding of how it works. And maybe you find it doesn't work for this particular situation. It doesn't work with this browser. It doesn't work with Safari or something. Or you find it doesn't work when you're offline for brief periods. And you end up heading that off by discovering that early on, rather than letting it bite you. So it's a matter of risk management for technologies. It's really important. Another thing is stakeholders' needs change. Stakeholders, it's not just that they can't conceptualize it early on. Their needs turn out to be quite different because of something that's occurred in their business context. You always have something to deliver for them. They have a sense of forward movement on that project, right? They have a sense like things are happening. I remember, going on 15 years now, I was flown overseas to do some consulting to figure out why a software company was having such major problems. Its customers were extremely unhappy with the software company, and I was looking to try to debug their development process. And a lot of it was that they just weren't delivering value incrementally. So it was always, well, in 6 months we'll give you this, in a year we'll give you this. And during that time, the host company, the client, would get impatient and their needs would change. So they'd say, well, look, you're taking a full year, you could do this as well, you can do that. And it turned into this thing where they could never really deliver the full project because they're always in churn with new requests. And they ended up, not having favorable customer reviews at all because of because the client was perpetually unhappy and therefore perpetually piling on new requests. What else might incremental delivery give you? Why else? From a developer perspective, pretend, the client is yourself or something for a moment. Putting aside stakeholder concerns, client concerns, why else would incremental development be good?
Smaller steps for integration.
Smaller steps for integration. With the waterfall model, one of the big things that can happen is the big bang. Oh, it's great. Here from now, it's great. It's great. Okay, so you have many people working on these things. We're gonna, when we put these together in a couple months' time, it'll be great. And often when you put them together, that's when things start going really bad. Perfectly reasonable assumptions made by X and Y, but they don't work together. They don't play together well. Or you discover that they have duplicated code. After a couple months of work, right? Discover the technologies are incompatible, whatever. The point is that if you can do the integration on an ongoing basis and actually sync it up, get it stable, robust, do the testing, do the peer reviews, you're in a much more confident, resilient, robust condition than if you just leave it to all be put together after a couple months. But more than that, folks, and we're going to come back to this in the estimation side. People are horrible about estimating the amount of time it takes to implement big chunks of code, big chunks of functionality. We could just fool ourselves terribly. Sometimes it's tied up with our sense of self-work. Oh, come on, I can do that in 2 months' time or something. And we just fool ourselves. We're horrible at it. We're horrible at estimation. I'll show you the statistics later. It's just unbelievable. We're over-optimistic, and our expressed uncertainty is much tighter than it should be. In other words, we're much more confident about the accuracy of our estimates. Our estimates are horribly underplayed. And if you're estimating smaller bits of work, we're much better. If you have to deliver every week a cycle, look, there's only so many days in this week. On Friday you're going to be out for this person's wedding. And Thursday you're going to have to work a shortened day because you got to drive there. And you get very concrete in your thinking. You get very concrete in thinking about what I need to do during this week. And your estimates get much more accurate. If you're doing it over 6 months, you could just fool yourself. Over 6 months, the estimates that are involved are often highly unreliable. So I want to see those incremental milestones, okay? Another thing, though, that goes along with this is continuous integration. Now, in 370, did you folks do continuous integration? Okay. So what do I mean by continuous integration? I mentioned the term early on the first day, just briefly talked about it. But what is continuous integration? What does it involve?
Daily builds.
Yeah, at least daily builds. At least. These days, the builds are often continuous. What do I mean by a continuous build? Does it mean it's just constantly churning, recompiling, and recompiling?
Every change is.
Every change that occurs, it does a new build. What do I mean by build? Let's be very concrete. What do I mean by build that does a new build?
Like a runnable execution.
Yeah, so it's not just compiling. Compiling is part of it, right? But compiling is just the start. Often it will run a suite of tests. For example, unit tests, system tests. Tests will make sure the different modules of the system hang together. Tester UIs that will put the system through its paces and common tasks. Regression tests. What's a regression test? Anyone remember from 214?
Retesting older code.
Okay, it has to do with old things, but what are the key things we're looking for in a regression test?
When you got something new, it doesn't break something.
We want to make sure that our existing features don't break. And what's the other thing we're looking for? Old bugs that have been fixed that they don't resurface. Why would an old bug resurface? After it's fixed, it's fixed. How if someone rolled back and checked in the old code? Can you imagine that? They do some work, they check it in, turns out it doesn't work. They say, oh man, I screwed up on that. I'm going to roll back these portions of the code. And they reintroduce this bug that was fixed earlier. You think that happens a fair bit? Yeah, it actually happens a fair bit. And we break earlier functionality. Which is bad, which is worse for the user? Breaking new functionality, or new functionality that doesn't work, or old functionality that breaks? All the functionality that breaks is much worse. They're counting on those features. You're using them in your day-to-day work, and suddenly this feature doesn't work that you've been using. You're up a creek. You've delivered negative value, not just you haven't delivered properly in the new features. You've delivered negative. You've taken away their ability to do the work. The previous version worked better, right? So continuous integration involves these builds, involves these tests, involves a smoke test, just to test if the system is sane, a test that is evolving. I talked about that briefly on the first day. But more than that, ladies and gentlemen, often the build is going to do further things like deployment of the system. What do I mean by deployment? So it builds, it runs a bunch of tests, assuming things are going fine, runs a bunch of tests, and then it may do deployment. Think about a web system. Why would you do deployment? Well, you put it out to test servers. So you put it onto a couple test servers where the testers can have at it, bang it, and so on. You actually put it out there. Now, if the build breaks, you don't put it out there, right? Another thing you might do is recreate the database, the test database, from scratch. Why from scratch? Well, if you don't do it from scratch, it might not be reproducible. You're still using what changes that were in the database earlier. You want to sort of do a complete refresh of the system and see if it's working okay. So these builds in continuous integration should be triggered by check-ins. More than that, ladies and gentlemen, mark my words. Mark my words. People in the team should be doing refreshes of their code base at least once a day. They should be pulling down the new check-ins by others. Why? Why? Why should they be doing that? So Bernd here does a check-in, and then others on his team want to get a refresh of that once a day. Why would they do that? Why not just wait for a week?
Catch merge conflicts early.
Exactly. Merge conflicts are one thing. So maybe some of his check-ins conflict with yours, right? Your name? Matthew. With Matthew's. Or maybe his changes are going to break the code that you're writing. And you want to know about that as soon as possible. In other words, your code's counting on things that his code is deprecated. He's checked something and now your code, the strategy you planned for doesn't work, right? Maybe he's removed a method that seemed unneeded to him, or he's merged it with another method to be more efficient. And now suddenly, Matthew, your code was counting on that method. It's removed. The sooner you know that, the better, right? Because you might have to throw away some of your code otherwise. And you don't want to have to do rework. You don't have to want to throw away code and so on. So the sooner you know that, the better. So if you can get other people's check-ins, you can save yourself a lot of grief and do them frequently. Do them early, do them often. Now, as far as you checking in, you check in when a chunk of work is done. And it should be a pretty small chunk of work. It might be within the course of a day. It might be every few days at most. But you shouldn't go weeks without it. Shouldn't go weeks without checking it. You should be doing it at least every few days. But the daily thing at least should be the refreshing your code base to get the changes of others. Because you don't want to be in a situation where you write a bunch of code and it has to be thrown away because someone already did it, or because you've been counting on things that are no longer the case. These things happen a lot. You can avoid them by the simple practice of checking in frequently. Okay. Why else continuous integration? Well, quicker identification of problems with functionality, quicker identification of new bugs, right? May not just be a matter of merge conflicts. It may be that the system isn't working and you've discovered it sooner. Again, your functionality doesn't work with Bernd's properly. Okay. You can spot problems with the smoke test. Again, what's the job of the smoke test? How is that different from a regression test or a system test? What's the job of the smoke test?
Just checks for the most basic functionality.
Yes, it tests for the most basic. It's not looking for, trying to track down new bugs or something. It's basically saying, is the system sane? Because if a set of check-ins have disabled basic functionality, like you can't even log into the system, then you're in a bad way. You don't want other people on your team to get that, right? You don't want them to get that because then they can't do their testing. You can't even log in. How can you run functions? How can you run certain functionality? So the smoke test basically checks, is this system sane? Is it in a sensible state, or something so broken that we don't want people to refresh off this code base? That would count as breaking the build. Just like a system that can't compile, you don't want them to refresh their code base. Does that make sense to you? Like, if the current state on the SVN or Git server is such that you download it and it hoses your code base, so now you can't even do testing of your own code. You can't even do some basic testing. You can't do further development in a way that allows you to run the system. You're in a bad way. You'd much rather the system basically be in a situation where you can still get your work done. And that's what the smoke test helps prevent, okay? Helps prevent this needless breaking of the code base. It also helps force developers to fix bugs before developing new code, ladies and gentlemen. You don't want someone who checks in a bunch of broken code and goes on and writes more code. They've got to get it fixed. They've got to get the system back in a sane state before they can push forward, okay? This is a problem historically with developers. They like to write new code. They don't want to have to deal with the corrupt from the old code. And we need to be more mature than that. Okay. I think that's time is up here. We're going to talk about levels of code and check-in here, but you might want to look through this stuff on daily integration. Okay, and we will continue on to discuss elements of mini milestones and progress reporting within our next time, and then go on to discuss some aspects of estimation. Okay, very good. Most of the teams, I know at least some teams have selected a project. I would like to know when you do select a project, I'd like you to notify me so I can plan accordingly. I can coordinate with stakeholders if needed. And again, if you need the tech stack, you folks should be thinking about getting infrastructure set up. Apache Tomcat servers, Postgres databases, virtual machines to run them, installations, Van Hibernate, whatever. If you're going to do that, what you should do is you should send mail to the tech staff, CC me, say you're a 371 team, they're used to this. At this time of the semester, needing things set up, just CC me so they know it's all approved. And if you have problems, let me know in terms of delivery, and I'll see if I can poke them a little bit. But you should feel free to send the mail directly rather than going through me, because I'll be a bottleneck with a lot of requests, okay? If you need to know who to send to, Greg is for setting up servers. Merlin typically does certain virtual machines as well as Windows type work, some configuration. But if you send to Greg and Merlin, or just to tech staff at cs.ustas.ca, that could work quite well. Okay? So please be encouraged to do that. Thanks.